Okay, AP Chemistry students, this is a continuation of our buffer discussion. So this is going to be a video talking about the Henderson-Hasselbalch equation and showing you equations or examples of calculating buffer solutions, as well as talking near the end of the video about buffer capacity. So in terms of an easier way of calculating with buffers, we can use this equation here called the Henderson-Hasselbalch equation. So in the Henderson-Hasselbalch equation, if we know if we know the Ka of something and we know the concentrations of its conjugate and the weak acid, we can calculate a pH. And this is a very good equation to memorize. I would actually recommend that you memorize this equation. It is not on your gray sheet, but it could be used in very quickly for pH calculations on the AP test. It is where the pH is equal to the pKa plus the log of the conjugate base over that weak acid. Or if you're talking about the weak base over its conjugate acid. So I kind of have it down here. As you can see here in another form where it's the base over the acid. Now, I want to go back to a little bit when we were talking about buffers, and really what is in one of the problems, we had the concentrations equaling the same. I believe that they were in an acetic acid buffer with a sodium acetate as the conjugate. You had concentrations that were both 0.5 molar. And I just want you guys to recognize that using this equation, if that happens and this becomes a big fat 1, when we take the log of that, so the log of 1 is 0, and in that case then the pH is equal to the pKa. And so it can be very quick to calculate a pH if you know the Ka values and the acid and its conjugate base are at equal concentrations. So it's a very useful equation. I really recommend that you get to know it. What I want to start out with today is showing you some calculations on how we would do buffers. I'm going to do it two ways. The first way I'm going to do it is I'm going to show it with the original what we would call rice tables, and then I'm also going to show with using the Henderson-Hasselbalch equation. Either way is acceptable for the AP test, so either way is good. Here's the problem. Let's say it's asking you to calculate the pH of a 0.75 molar. Now, hopefully you're recognizing that this is an acid. You see the H here, and then you can see that there's the conjugate base. And so you can know that this is an acid, and knowing that this is an acid, we're going to write out the equilibrium expression. So it's going to be HC3H5O3, and that is going to dissociate into the hydrogen ion, and you're going to get the C3H5O ion. Okay, so initially this concentration, so here's my I, initially this concentration is 0.75, this is 0, and then this is 0.25, and remember this is 0.25 from the conjugate of the salt, okay, from that sodium C3H5O3. The change is going to be that it is going to dissociate, so these become plus X, and then the equilibrium line would be 0.75 minus X, this would be X, and this would be 0.25 plus X. So now, if we were to put this into the equilibrium expression where we know that Ka is equal to the hydrogen ion concentration times the C3H5O3, oops, I should have a 3 here, I just noticed that, okay, over the acid, okay, and we substitute in what we know that this is 1.4 times 10 to the negative 4 is equal to X times, let's see, this is going to be 0.25 plus X, and this is going to be 0.75 minus x. Now, again, if x is small and we can ignore the value of x, that's going to become 1.4 times 10 to the negative 4 is going to equal x times, let's see, this is going to be 0.25 over 0.75. So you have that kind of fraction here. When you solve for x, x is going to be 0.00042, which is molarity, which is also equal to that hydrogen ion concentration. So we can say that pH is going to equal, and again, you'd have the negative log, you got to show the substitution, 0.00042. You would end up with a pH of 3.38 in this concentration. So you went through and you showed the calculation for, using the rice tables. Now, another way that we can do this is we can do the same problem showing and I'm going to do this in black so you can see that there's a difference. We can use the Henderson-Hasselbalch equation. Now, the Henderson-Hasselbalch equation says that the pH is equal to the pKa plus the log of the conjugate over the acid. So, the first thing I would have to do is I know what the Ka value is. It's 1.4 times 10 to the negative 4. So what I'm going to do here is I'm going to say and show the work for calculating the pKa. Just like a pH, it would be the negative log of the Ka value, which is 1.4 times 10 to the negative 4. So when I do that work, I come up with 3.85. And I'm going to extend this out a little bit just so you can see that the equations, that the numbers come out exactly the same. So I'm not changing or using any significant digits yet. I'm just kind of extending this out because I'm now going to calculate the pH by plugging in, saying that, okay, the Ka there is 3.85387, and I'm going to add the log of the concentration of A minus right here, which I know is 0.25 over the concentration of 0.75. Okay? So when I do this work, I end up with 3.85387 minus 0.477. That's the simplification of the log of 0.25 over 0.75, which then makes this become 3.38, which is exactly the same pH as what you had here. So it is a little faster if you know those concentrations. So, feel free to use it. The AP board knows the Henderson-Hasselbalch. It's just the shame that it's on your gray sheet. So you do have to memorize it, but it's not that difficult. All right. The next one that I want to show you then is that we can calculate buffers when we're talking about weak bases here. Let me get to a different color. So when we're talking about weak bases and we're calculating the pH, now it's asking me to calculate the pH of a 0.25 molar NH3. I'm giving you the Kb and the concentration of the ammonia chloride solution. So when we're thinking of this, again, major species, so things that are used, that you're seeing that are floating around in that water would be that weak base staying together because it's weak, and would be this, the NH4 plus, and the Cl minus, which is coming from that species right there, and you have water. Okay, so now from this list, you should be able to say what is controlling the pH. And what is controlling the pH and what you should write your rice table based on is that base. So when we're writing a base with a rice table, the equation, I recommend that you do add the water. The water is a liquid in your rice table, so it's not going to have any values, but it does help you to understand, again, remember that you are making a base. So there's OH in there. So here, the water is donating a proton. That's where that OH is coming from. So when I do the Rice table here, this initially is 0.25. There's nothing that goes in that water line. This is 0.4 because it told me this is from the dissociation of the ammonium chloride, and this will be 0. What's going to happen is that this is going to get consumed. We're going to be adding these, and here I get 0.25 minus x, 0.40 plus x, and this would be x. So now when we're looking at the Kb expression, the Kb is going to equal the concentration of MnH4 plus times the concentration of OH minus. And the reason why I'm spelling this out is don't be fooled when you're talking about bases. Remember, you're not making acids, you're making hydroxides. So you have to account for that. When I plug this in, it becomes 1.8 times 10 to the negative 5 is equal to 0.40 plus x times x, which would be the hydroxide ion concentration, over 0.25 plus x. Now, because of this Ka value and looking at our concentrations, we can ignore these x's and we simplify this and we can say that x is equal to 1.1 times 10 to the negative 5, and that would be in molarity, but remember, this is hydroxide ion concentration. So if we were to take the negative log of 1.1 times 10 to the negative 5, we're not going to get a pH, we're going to get a pOH. And here the pOH ends up being 4.95. And then to find the pH, we're going to take 14 minus 4.95, and you end up with a pH of 9.05. Okay. Okay, so the alternative way that I want to show you on how we can do, how we can solve this if we have a 0.25 molar NH3 and a 0.4 molar NH4Cl is with the Henderson-Hasselbalch equation. I went ahead and put it in blue there so you can kind of see. Here's the Henderson-Hasselbalch equation, but notice that this is for an acid species and we're dealing with the base. So when that's the case, you have to convert to a Ka. Got to convert that Kb to a Ka, which I did. And then I took the pKa of that Ka and I got 9.9225. So now when I add that into the Henderson-Hasselbalch equation, I can say that the pH is equal to 9.255 plus the log of the base over the acid. And if you look back up at the original problem, the base was 0.25 and the acid was 0.40. So when I do this, I get 9.255 minus 0.204, which gives me the same pH. So see how those are the same. So the only thing you really have to watch out for if you're working with a base and you want to use the Henderson-Hasselbalch equation is that you got to make sure that you convert that Kb over to a Ka by using the Kw equation right here. And you'll end up getting the same value as well. All right, that's about the end of my time for this. I am going to add buffer capacity onto another slide, so you can watch for that next.